And before we dive into the topic of today, I have a few practical announcements to share with you. So I'll start by sharing my presentation. Okay. Let me try that again. All right, I should be able to see my presentation on the big screen. Let me know if you can't. All right, so this is the second week in the semester. We're going to wrap up our probability theory lecture. And this week is also the first week that you have some actual written exercises. So as you saw from the email that I sent out over the weekend, or well, was it yesterday? I forgot. Since so many of you expressed a preference for having the classes take place online, the theory classes, that's not a problem for me. We will just continue online. So I've set up the Euphora invite in the calendar for regular theory lectures online. And we'll stick to the same schedule. It's just going to be online. If you have any doubts about that, if you feel like, hey, I really learn much better in class, come and talk to me and we can see if we can figure something out. So I don't want to shut the door on in classroom teaching, but given that the situation is changing so rapidly in Korea and that you have expressed a preference for having online teaching, that's what we're going to do for now. And then the written exercises, that will not change. That will still be on campus, divided over two groups of about 35, 36 people each. And here, so those will take place basically at the same time as the exercise sessions did last semester. So from Thursdays from 8:30 in the morning until 11:15. If you check Euphora, you should be able to see which group you are in. And the first group, group 1, will go to auditorium B1 for the exercises, and the second group will go to auditorium GH201. And so, as I mentioned, about 35 people per group. And then last, the schedule for this week. So what are we going to do this week? We will wrap up our admittedly very short chapter on probability theory. There's a lot more that we could discuss, but we will just cover the fundamentals. We've talked a little bit about discrete random variables last week. We finished off with an exercise. There's one more calculation that I want to do there, the mean of a binomial variable. And then also I want to talk a bit about Poisson random variables. And then we'll move on to continuous random variables. And that's also going to be more or less a survey of what you already, or a repeat of what you already know. So that's going to be quite straightforward. And then we'll wrap up the class for today with hypothesis testing for a proportion. So we'll use that opportunity to go back to what we learned in the first semester, i.e. hypothesis testing, and we'll use this particular test. Sorry, someone is trying to convince me to vote for a president that, or an election that I can't vote in. So yes, where was I? Hypothesis testing. So yes, we will recap a bit what hypothesis testing was about. We'll apply it to this particular case, and then that'll be it. And so on Thursday, you have the written exercises. So there you'll do all sorts of calculations to practice it. You'll see it's a lot of variations on what we cover in this lecture. And next week, finally, we'll move into, which is going to be the big topic for this month or this block, regression analysis. Those are all the practical announcements that I have. Any questions or any comments so far? If not, I have an activity for you. I will stop sharing my screen and I will go to the browser and share my screen again. And I want to play a short quiz with you. So I want you to, if you can see my browser, you should be able to see a URL that says www.wooclap.com/UK-poll. And I want you to go to that link address. So I'll also paste it in the chat here. So if you just go to that address, what I want to do is I want to run a small poll, and I'll tell you what the poll is about later. So this is not for a grade. It's just basically recapping what we did last week and talking about that for a little bit. So it's the first time that I do this, so bear with me if it doesn't go right the first time round. If I go here, we should be able to have the first question in our poll. So the first question in the poll you should be able to see on your screen now is, if you toss a coin twice, what is the probability of getting 2 heads in a row? So you take your 101 coin, you flip it twice, and you want to know the probability of having 2 heads. So I will maybe, in order not to bias the results, I will go to another tab and give you a little bit of time, to a couple of seconds to answer that. So think about what a fair coin is, what it means to have 2 heads, and then try to put a number on that, or say, yeah, I don't know, or it's not that. So I'll count down 5, 4, 3, 2, 1. And let's have a look. So almost everybody voted 25%. That is exactly right. So I think this was an easy question for you. The probability of having 1 head is 50%, 1/2. Since the 2 coins are independent, you multiply the probabilities and you get 1/4, or 25%. And then the second question is about diagnostic testing. So suppose you have a diagnostic test for a virus, let's say COVID, and the false positive rate of that test, so the proportion of people that don't have the virus but do get a positive result, is 1 in 1,000. So that's the false positive rate. And you have taken the test and you have tested positive. What is the probability of actually having the disease? So I will also let you ponder on that, maybe for a couple of seconds, 30 seconds or so, and then we'll have a look at the results. All right, I hope you had a chance to answer. Let's have a look at the results. So we get a lot of people answering 99.9, and then a few in the other buckets as well. So does anybody want to maybe unmute and say why they chose one of the 4 answers? do you want to defend your answer and maybe justify why it's 1, 2, 3, or 4?
So I picked number 2, and the probability of false positive result is 1 over 1 over 1,000. Okay.
Mm-hmm.
So the real positive rate will be 1 minus 1 over 1,000. So I calculated that. So the real positive, the probability of real positive is 999 over 1,000. So this is 99.9%. So I calculated like this.
Okay, that is a valid calculation, but you have to be a bit careful about what you end up calculating. So that will give you indeed the complement of the false positive rate. So what that 99.9% gives you is the people without the virus that get a negative result. And here what we want to know is, I don't know my disease status. I could be positive, I could be negative. The only thing that I know is that I have a positive test in my hand. So as a matter of fact, what that means is that the correct result is number 4, the not enough information to know, because remember from last time, if we have a diagnostic test with a given false positive rate, we need to know the prevalence in the population to decide what is the positive predictive value, what is the probability of having the disease given that I tested positive. So the correct answer in this case is number 4. And now, why do I ask you these questions? And you might have guessed it from the title of the poll, UK poll. So these 2 questions were asked amongst a bunch of other questions from UK politicians, members of parliament, a few months ago. And let me see if I can find the press release. I had it in a tab, but then again, I have a lot of tabs. See if I can quickly pull it up. Okay, sorry, I was digging through my inbox. I should have had this tab open. So what happened is that the Royal Statistical Society in the UK asked MPs precisely these questions that you answered. And the results were actually quite bad, given the fact that these are people in positions of power, and that there's a pandemic going on, a pandemic that requires a lot of numerical insight in order to make policy decisions. So the question that you guys all had right, the one about the coin toss, was only answered correctly by just over half, or 52% of MPs. And then the other question, the diagnostic test, where is it? Here, the results were even worse. Here, only 16% gave the correct answer. So that's not to put blame on anybody. MPs have to wear a lot of different hats, and they can't be expected to memorize everything. But if you came out of last week's lecture thinking like, oh, hey, this Bayesian diagnostic testing, that's easy, that's great, because it's a useful tool that you can use for decision making. And so we have the press release ends with a statement that says, yeah, statistics is good for decision making and scrutiny of data. And they admit, yeah, MPs' knowledge has a little bit improved. So parliamentarians' knowledge has improved a bit, but more needs to be done most of the time. I'll share the link with you. There's a few more questions, all of which I think you can answer with what you know, either from last lecture or from the current lecture. All right, that was just a small diversion. And let me then pull up my presentation for the rest of today. So if you bear with me just a second while I set things up. Okay, you should be able to see my screen. Give me a shout if not. And we'll continue with where we were last time. So just as a quick recap, what we were doing last time, we were talking about discrete random variables, which are random variables that take on a finite or a countable number of values. And the archetypical example here is counts, counting things and then assigning a probability to given counts. And in particular, we were looking at the binomial distribution, which gives you the number of successes amongst a set of trials. So you toss 4 coins, and each coin has a probability of P equal to 0.50 for a fair coin to land heads. And then the question is, what is the probability of seeing K heads? Question mark. And here K can be 0, all tails, we don't see any heads. Can be 1, just 1 head, 2, 2 heads, 3 heads, or all heads, 4 heads. So here the possible outcomes are 0, 1, 2, 3, 4. So we'll look at this particular example, and then we'll also have a look at the Poisson distribution again. So to go over the assumptions that go into Poisson, into the binomial distribution one more time. So what we have is n independent observations, n coin flips, or n things that can change independently. And each can be in two states, success or failure, on and off, cancer cell or no cancer cell. So two possible outcomes, with each success governed by one and the same probability, P. So this is why I keep using this coin toss example, because if you take 4 coins all with the same probability, that's a very natural binomial process. But another example could be, for instance, if you have probability of developing cancer in a certain group of people in the population. If you stratify so that everybody in your population is more or less the same, then probably the probability of developing cancer is going to be the same for those people, like if you sort of rule out environmental factors. And then there you could also probably model the number of patients as a binomial distribution. Another example that we'll see in at the end is if you have a production process in a factory, and let's say your factory has a machine that makes widgets, or that makes drugs, or that makes some kind of food item, then the machine is probably not going to make all of those things completely perfect from the first try. It's probably going to have a certain defect rate. So a certain number of the widgets or of the things that the machine produces are going to come out defective. And under some limiting assumptions, you can also model that as a binomial process where you say each widget that comes out of my machine has a probability P of being a defect. And therefore, the total number that comes out of the machine is governed by a binomial distribution. And for the probability distribution of the binomial distribution, we said that, well, the probability of seeing exactly k successes out of n trials is given by the expression down below here, where n choose k is the binomial coefficient given by n factorial k factorial n minus k factorial. And why does that binomial coefficient show up? It's because you're interested in how often do I see k successes out of n failures? Well, we only care about the count. We don't care about the exact distribution of which trial was a success or a failure. So it turns out there are n choose k, given by the binomial coefficient here, possibilities of organizing the successes and the failures. And last time we sort of sketched out if you have 3 trials and you have 2 successes, there are 3 possible ways of organizing those 2 successes. And we sort of hinted a bit at how the binomial coefficient comes up. So that explains the binomial coefficient. And then the other 2 terms, the p to the k and the 1 minus p to the n minus k, those probabilities, where do those come from? Well, the p to the k is the probability of having k successes. And then the 1 minus p to the n minus k is the probability of n minus k failures. So if you want to have k coins heads up, then you also have to have the complement n minus k heads down or tails up. So p to the k gives you the probability of having those k successes, and then 1 minus p n minus k gives you the failures. And now the calculation that I want to do with you is the calculation of these two population parameters, or at least the one of the mean. The variance is going to be the same, it's just more involved and a bit more work actually. So let's look at the results. So here, what this result says is that the mean of a binomial variable is given by the number of trials n times the probability of success. And that's something that intuitively you know. If I say, well, I have a, or let's not use the coin as an example because that gets boring after a while. Let's say I take a test and the probability of having success on my test is 20%. Let's say I didn't study a lot and I have probability of success 20%. And now let's say I don't just take one test, I take a bunch of tests. Maybe I'm going through a cycle of exams and I take 10 tests in total. So 20% is probability of success in the literal sense in one exam. Then if I take 10 exams and I have a probability of passing of 20% in one exam, then you'll probably agree with me that the total number of exams that I expect to pass is going to be n times p, so 10 times 0.20 or 2 exams in total. That this is fairly straightforward if you think about it from daily life. So, but we don't want to just rely on our intuition. We are scientists. We want to have incontrovertible proof that this is indeed the mean or the expected value of a binomial distribution. So let's derive that n times p from first principles. And for that, well, what I'm going to do is I'll take a random variable x, which is distributed according to a binomial distribution with n trials and probability of success p. And I'll compute mu, which I'll also denote as the expected value of x. So I think we saw this notation in passing a while ago, but this notation means the expected value. In other words, the mean, the average, those are all synonyms. And what is that? Well, I know from a couple of slides ago that the mean of a random variable is what you get if you take the probability of an outcome, you multiply it by the outcome, and you do that for every possible outcome, and you sum all of those things together. So here the little p's are the probability of having outcome x1 up to xk. So we multiply probability by outcome and then sum it all together. So let's do that. So I'm going to want to sum things together, and I'll leave the summation a bit unspoken. So I have the probability of having a certain count k times the count itself, so times k. And now what do I sum over? Well, I have to sum over all possible outcomes. And if for a binomial variable, I can have 0 successes, I can have 1, 2, 3, and so on, up until n successes. So here the summation runs from 0 up to n. And now let me rewrite that in a very similar looking way, but something that's going to help us. Let me rewrite this as follows. So I'm multiplying pk, probability of seeing k successes, by k. And k can go from 0 to n. So if k is equal to 0, the corresponding term p0 times 0 disappears because you multiply by 0, and that falls out of my sum. So what I can do is I can write my sum as sum not going from k0, but from k1 up to n, and then pk times k. So that's a lot of words just for a small manipulation. There's one term in that sum that's always 0, the one where you multiply by k is equal to 0. Okay, so far so good. Let's write out what this gives me. So let's substitute what we know about the probability. So I have sum k is 1 up until n. Binomial coefficient n choose k. P to the k, 1 minus p to the n minus k, and then times another k. That's a bunch of stuff, so let's try to simplify it. And the first thing that I'm going to do is I'm going to look at the binomial coefficient and that extra k together here. So let me maybe do that on the side. I have two terms there, n choose k times k, and I'm going to treat those separately for a moment. So let's use the definition of the binomial coefficient. So I have n factorial, k factorial, n minus k factorial, and then times another k. So just expanding the definition of the binomial coefficient. Okay, and now there's one more thing that I can simplify here. So, you know, k factorial, that is k times k minus 1 times k minus 2, and so on, descending numbers until you get 2 times 1. And the simplification that I want to make is, well, now I've got a k in the numerator and a k in the denominator. So those two cancel against one another. And if I assemble everything back together, and let me put a bit more space, then I get n factorial here, k minus 1 factorial, n minus k factorial. If you think back about your days in Math 1, when you saw the binomial theorem, there are a couple of exercises along those same lines. So maybe you did exactly this calculation then, but even if you didn't, if you think back about those definitions, then you can see what we are trying to do here. So now let's go back to the expression that we were trying to calculate, and let's plug in what we just found. K is 1, n factorial k minus 1 factorial, n minus k factorial. And then I still have p to the k, 1 minus p to the n minus k. And now I'm going to do another step, which may seem a bit strange, but that's going to make a lot of sense. So now the second simplification that I'm going to make is, I have that summation k from 1 to n. I'm going to rename the summation index, and I'm going to introduce a new index called L, which is k minus 1. So that's the definition of L. So if k is equal to 1, then L is equal to 0. And if k is equal to n, L is equal to n minus 1. And now let's rewrite everything in terms of L. So now my summation is going to be over L, and it's going to go from 0 to n minus 1. And what do I have everywhere? Where I have n factorial, L factorial. Now I have to be a bit careful. I have for the third factorial n minus 1 minus L factorial, because k is L plus 1 and n minus k is n minus 1 minus L factorial. And now I have p to the k, so that's L plus 1. And then I also have 1 minus p, and that's another n minus 1 minus L. And this is already starting to look maybe a little bit like something that we could do something with, because if you look at the terms here, then what I'm starting to see is something that looks like another binomial coefficient, except I'm starting to see a lot of n minus 1s. I have an n minus 1 here, I have an n minus 1 here, and I have an n minus 1 here. And what I also have, if I have more colors, is that I'm starting to see a lot of L's. So I have a summation over L, I have an L factorial minus L. Here it's a bit, I have an L plus 1, so not just L plus 1, but that's fine for now. And I have another L here. So let's try to roll with that intuition and try to write everything in terms of n minus 1 and L. So what I'm going to do for the next step is I'm going to focus on a number of things in my expression. This n factorial, I'm going to write that as n minus 1 factorial times n. And this p to the L plus 1, I'm going to write that as p to the L times p. So then this is probably going to be the last expression that I write down. But what I'll also do is you have that n here and that p. They don't depend on L, they're just constants. So I'm going to take them out of my expression and write n and p. So I've already taken those out and I put them in front of the summation. And now my summation becomes sum from L0 to n minus 1. I have n minus 1 factorial, because that's what's left of my n factorial. I have L factorial. I have n minus 1 minus L factorial. And then times, and I'll have to write it on the next line here, times p to the L minus 1. No, sorry, that's not right. P to the L, because I started with PL plus 1 and I split off 1p, so I get p to the L, and then 1 minus p, n minus 1 minus L. Okay, let me maybe put parentheses around this whole expression, like so. Okay. And now I claim that we are done and that we have the result that we were trying to get at, which is the n times p. And why is that? Well, everything that you have in the summation, that entire summation, that is just equal to the constant 1. And why is that? Well, if you think back about the binomial theorem, then what the binomial theorem told you is if you have a sum of two things, and I will write down what that sum is in this case. If you have a sum of two things, p plus 1 minus p, sorry, I keep miswriting, 1 minus p, and you raise that sum to a power, in this case, n minus 1, then the binomial theorem gave you an expression, a sum of terms involving binomial coefficients that expanded that power. And if you look long and hard at this messy expression with summation, then you'll see it is precisely what the binomial theorem gives you. So here we're not using the binomial theorem in the forward direction, taking x plus y to the n and expanding it. We're taking the expansion and we're contracting it. But this follows by the binomial theorem. And just as a reminder, what does the binomial theorem tell you? Well, it tells you that x plus y to the power m is sum L equals 0 to m choose L, x to the power L, y to the power m minus L. That's the binomial theorem that we know and love. So here, in order to make it work out, x is p, y is 1 minus p, and m is n minus 1. So if you substitute those values, you'll see that you get precisely what we simplified here in this expression, the one that I'm highlighting now. And now, if you look at, for the last step, if you look at what's between parentheses here, p plus 1 minus p, that's 1, raised to the power n minus 1, that still is 1. So this whole expression is equal to 1, and we end up with n times p as our result. So we get the expression for the mean. It's a little bit messy, but if you follow the steps and maybe if you write them out for yourself one more time, then you'll see it's sort of all matches and telescopes together to give you precisely n times p. We're not going to do the expression for the variance, but you should know and be able to apply this expression in exercises. So here the variance of a binomial variable is n times p times n minus p. So also a very short expression involving the probability p and its complement. So to give you maybe a couple of minutes to finish jotting down your notes, are there any questions at this point about this calculation or about binomial variables in general? I'm keeping an eye out on the chat as well. Okay, so if not, then we had the exercise that we did last time. I will skip over this because it's fairly well worked out in the notes of last time, and I will reconcile this with the notes that we made last time. The only thing that we didn't do last time is what number of lymphocytes do you expect on average? Well, if we have that the number of lymphocytes is a binomial randomly distributed variable, then we know that the average, the expected value is n, which is 10 times the probability of success, which is 0.20. So we expect to see 2 lymphocytes amongst the 10 here. Maybe just coming back to this computation. So I get a question, is there a difference between n in my slides and n written like this? No, there is no difference. All n's here are the same. So they are all the probability of, or the total number of trials. So n written like this is n written like that. Okay, so then one other random variable that is worth keeping in mind is, or one more distribution is the Poisson distribution. And why is the Poisson distribution useful? Well, this models, again, counts, but now no longer counts where you have a fixed number of trials and you want to know how many successes there are, but counts in a given time frame or in a given area or in a given length scale. And you'll see a lot of examples during the practical session on Thursday, but there's already a few in this session as well. So for instance, here we have a set of aerial photographs of seals in Alaska, and we want to model the number of counts or the number of seals across a given area. And then what we basically have is that the number of seals will, to a good extent, follow a Poisson distribution. And what does that mean? Well, you have a graph of a Poisson distribution here on the right. And the characteristics of it are, if we think about it, that if you take one island and you count the number of seals on that island, then the number of seals can be arbitrarily large. It can be 10, 100, 1,000, 1 million. A priori, there's no upper bound. Like you, of course, in real life, there is, like we can't shove millions of seals into one particular island, but we can imagine that the number of seals can become very large. But at the same time, we expect large numbers of seals on any one given island to be relatively rare. And you see that in the distribution, which falls off basically exponentially fast as the number of counts increases. So here on the x-axis, we have the number of seals on the island. And we see that the probability of having, let's say, already 30 seals is very, very low. And the Poisson distribution actually has infinite support. So it can tell you what the probability is of seeing 40 seals, but that probability is going to be even lower. And it's going to be so low that it's practically zero. On the other hand, what we see is that the probability here on the left-hand side of the graph increases until you hit this mean or this mode of 15. And that also sort of embodies what we expect from the number of seals. Maybe there's some mechanism, maybe they like to live in groups of a certain size that make living on islands of a certain size attractive for a group of 15. So if we look at another island of the same area, then we expect to see a number of seals. And it could be that there's no seals, but that probability is very rare. And it could be that there's 5 seals, and we'll see that a couple of times, but that probability again is quite low. So that's maybe trying to reason a bit through the example of the seals. And here the important things is you're looking at an island of a fixed size, and then you're wondering, like, what do I expect the number of seals to be on that island of a given size? But the Poisson distribution can do more than just count seals. It can also tell you something, for instance, about a number of events in a given time frame. So let's say you're running a delivery service. This is the next example that we'll do. And you want to know how many orders will I get within the next hour, or within a given time frame, the next day, or the next 5 hours. Then chances are that that number of calls or number of orders that you will get will be distributed with a Poisson distribution. And so to keep hammering on the analogy, there too, if you think about it, if you expect to have 50 orders per hour, there's no reason why you couldn't get 1,000 orders or 2,000 or 1,000,000. But those probabilities of having larger and larger number of orders are going to decrease exponentially fast. So to make it a bit more mathematical, we have here the probability distribution of a Poisson random variable. And that variable has one parameter, this lambda. And lambda, as the slide says, it is the expected number of counts per unit time, per length, per area, and so on. So for instance, if we look back at the previous example, here we see the average of the distribution is at 15 for the seals. So for seals on an island, here we would probably take lambda to be equal to 15. And then having that one parameter in hand, we can calculate the probabilities of seeing k counts. And the number of counts here, you have to be a bit careful. It can be 0, 1, 2, 3. But it can, for the Poisson distribution, it can be arbitrarily large. So the Poisson distribution allows you to say, what is the probability of having 75 billion seals on that island? And physically, that doesn't make sense, but mathematically it does. And all that the Poisson distribution is going to tell you is that, yeah, that probability is virtually 0. And then given lambda and k, the probability of having exactly k in your time interval or in your area and so on is given by e to the power minus lambda times lambda to the k divided by k factorial. And you might wonder, where does that come from? Why such a weird looking expression? Well, it turns out that you can mathematically derive that. We will not do that, but I just want to show you how this works. So let's return to our seal example. So for the derivation, we'll sketch this out. So for the seal example, let's say we take our island. And now we divide our island in a grid of cells, very small cells. If we make the grid small enough, then what we can say is, well, each cell in the grid is going to have either one seal or no seals. If there's 2 seals in one cell of the grid, it means our grid is too coarse and we need to refine it. But if we make it fine enough, then we can say there's going to be either 0 or 1 seal per grid cell. And so let's color those in. The ones that I color have a seal in them, and the ones that are not colored are free, don't have a seal. And then maybe my distribution looks like this. So this means seal, and empty cell means no seal. And now let's think a little bit about the distribution of the cells. So each cell can have a seal or it can have no seal. And that should start making you think about the binomial distribution or the Bernoulli distribution, where having a seal is a success and having no seal is a failure. So we have basically a binomial distribution telling me which cells have seals in them and which ones don't. So if I write this down schematically, so we can say, we can define this random variable xij is 1 if seal in cell ij, and 0 if no seal. And then what I have is that xij is a Bernoulli random variable or a binomial variable with one trial and a certain probability P of success. Okay, so now I have a Bernoulli random variable, success or failure. And now I want to say something about counts. So if I continue down below here, I want to know something about the total count of seals across the grid. So what I'm going to do is I'm going to sum all of these xij's. And I'm going to call that thing x. And that thing is going to be distributed, well, if I have n cells, that's going to be distributed as a binomial random variable with n tries, the number of cells, and a given probability of success P for each cell. So that gives me binomial random variable. I know and love binomial random variables, so I'm very happy with this. Now, the last step that I'm going to do, and this is the one where all the technicality is, now I want the grid to become infinitely small, because that grid was an approximation. What I want to know is, for finer and finer grids, what can I say about the count of seals? Like if I look at my aerial photograph, there's no grid sketched on that island. That grid is something that I invented. So now I want the grid to go away. And what I'm going to do is I'm going to make it infinitely fine, and I'm going to see what comes out. And it turns out if you do that, and if you do that in the right way, then what you will get out is a new random variable, which is going to be distributed according to a Poisson distribution. And if you keep track of where everything goes in the distribution of the x being binomially distributed, and you let that grid become infinitely fine, then you will get precisely this expression. So I'm sweeping a lot of technical details under the rug, and that's fine. I just want to tell you this is not magic. Someone didn't just think of this probability distribution out of nowhere, but it comes from very elementary considerations where you say, well, okay, I can have a seal or no seal, and what happens if I let that go to infinity? Okay. So I will go to the next slide. So you have to know the distribution of a Poisson random variable, but of course this derivation is just for illustration. We have the mean and the standard deviation or the variance of a Poisson distribution here. And this is very easy. Both the mean and the variance are equal to the parameter lambda that we already introduced. So this is very easy. It's just lambda. I want to maybe, to wrap this up, also derive why the mean of a Poisson variable is that parameter lambda. And fortunately, the calculation is a little bit shorter than for binomial. So let's have a look. So let's say I have a random variable that's distributed according to a Poisson distribution with parameter lambda, and I want to know the mean or the expected value. And again, what is that? Well, we have to sum over all possible outcomes, all possible counts. And now the counts can be 0, 1, 2, and so on, but they can be arbitrarily large. So I have an infinite sum here. And now what do I have to do? Well, I have to take the probability of having a certain count, e to the minus lambda, lambda to the k, divided by k factorial, and then times that outcome. So times k. And I'm going to do the same thing as before. So for k is equal to 0, multiplying by k destroys that term in the sum. So I'm going to write first and foremost this as k equal to 1 infinity e to the minus lambda, lambda to the k, k factorial times k. And now I can simplify a little bit. So again, I can combine the k and the k factorial, and I get k is 1 to infinity e to the minus lambda, lambda k, k minus 1 factorial. And now I'm going to do the same thing as what I did for the Bernoulli. And I'm going to introduce a new summation index, L, being equal to k minus 1. And so now if I rewrite everything in terms of L, I get sum L from 0 to infinity. So if k is equal to 1, L is 0. And if k is 2, L is 1, and so on. So that explains the bounds. I get e to minus lambda, that doesn't change. Lambda to the L plus 1. And then L factorial. Okay. And now let me rewrite that sum just a little bit. So first of all, I'm going to take out the e minus lambda because that doesn't depend on L. I can take that out of the sum. And secondly, I'm going to write lambda to the power L plus 1 as lambda to the power L times lambda. And so I can take out another lambda and write the sum as L equal to 0 infinity lambda to the power L divided by L factorial. And now I'm almost there, because if you think about things a bit, then what you have here should start ringing a bell. And now I wonder, does anybody want to take a guess, or do you recognize this expression from somewhere in your Math 1, Math 2 course? So I'll let you think about that for a little bit, but I'll also write it out not as a summation, just as a series. So if you write this out, this is 1 plus lambda squared 2 factorial lambda to the third 3 factorial, and so on. And this is no ordinary series. It has a very special interpretation. Does anybody want to take a guess? There are no wrong answers. Any guesses? Yeah, so I got one answer, the Maclaurin series for the exponential function. That's exactly it. So this is the Taylor or the Maclaurin series for the exponential function. You probably thought when you saw this, like, oh, that's abstract stuff. When am I going to use that? Well, this is exactly where you use this. I saw there was another answer pointing towards a power series or trying to connect this with the expansion of something raised to fixed power. That is not entirely correct, but you could make things work that way as well if you then take the power to go to infinity. But it's probably easier to link this directly to the Taylor or Maclaurin series because it's around 0 of the exponential function. So thank you for that, because now we can wrap up our exercise. So we have e to the minus lambda times lambda times e to the lambda, because that's the Maclaurin. And of course, those two exponentials cancel each other, and therefore we're left with lambda. And that gives you the expression for the mean. And once again, the variance, similar calculation, just a little bit more difficult. Okay, and then for the last part of this lecture, we'll look at an example. So this is just to get your mind off the seals. So forget about seals. That was just an example. Poisson distribution occurs in a number of different contexts. The example that we will do here is the delivery service. But there's another example that I want to just talk you through, which is a very useful one if you do molecular biology. If you have a DNA strand, let's say a chromosome or a part of a chromosome, then if you look at the mutation rate, then, and I'm going to simplify things a little bit. So each nucleotide in the DNA strand has a certain probability of mutating. And if you assume for a moment that that mutation rate is constant, which we actually know it isn't, but just to simplify things, let's take it to be constant for now, then the number of mutations that you get in a DNA strand is binomially distributed. But now DNA strands tend to be very long, thousands, tens of thousands, hundreds of thousands, millions of base pairs long. So there too, if you take the limits of like infinitely long DNA strands, then what you will get out is a nice Poisson distribution. So if you're talking about the rate of mutations of a DNA strand per length, chances are that you will see a binomial distribution showing up. We're not going to do that example. We're going to do something more pedestrian, delivery service. So we have a delivery service that receives on average 10 orders per hour. And we want to know the probability that they will get more than 60 orders over a 5-hour time span. So the running out of stock, let's say they only have 60 bowls of Yukijang in the freezer, and they want to know what is the probability that we'll run out of stock before we close for the day in 5 hours from now. Well, a couple of things are worth noting here. So we have on average 10 orders per hour. So we can say, well, we're looking at a Poisson process where lambda is equal to 10, but we have to be careful that is the rate per hour. And we're asked to say something about a 5-hour time span, so we're going to need a different time span. And luckily, what you can do is, if you know what it is per hour or per unit time, and you need a different basis, in this case 5 hours, you can just multiply the rate per hour by 5. So you get 50 for this rate. And this makes sense. If you expect 10 in 1 hour, in 5 hours, you expect 50. That's where that 50 comes from. And now, what is the probability of getting more than 60 orders? Well, that means we were asked about the probability that X, where X here is the number of orders over 5-hour time span, the probability that that is bigger than 60. And we can calculate that. We can either calculate it directly, but that would be a bit painful because then we would have to ask, what is the probability of 61 orders, 62 orders, 63 orders, and sum all of those infinite probabilities together? That's painful. So what we'll do is we'll write this as 1 minus the probability of the complement, which is less than or equal to 60. So X being bigger than 60 and X being less than or equal to 60, those are complementary events. And remember, the probability of an event is 1 minus the probability of the complementary event. And now, this probability is still hard to calculate by hand. I will not lie. If you do this by hand, then you have to write, well, this is 1 minus p, x is 0, minus p, x is 1, minus ... minus p, x is 60. And then you have to use the formula from the previous slide, 61 times, and sum it all together. So that's not going to work. What we can do instead here is use R. And in R, you can compute this probability by writing 1 minus P plus for Poisson. And then you supply the argument account that you're interested in and the lambda parameter, or in this case, the mu. So 50, and that's it. And that will give you the desired probability. And I will look at my screen. So if you calculate this correctly, you will get 0.07216 ... So about 7.22%. So there's a 7.22%. Now we'll get more than 60 orders over a 5-hour time span. Okay. So with that, we are at the end of discrete probability distributions. It's also 11:15, so I suggest that we take a 15-minute break here and return at 11:30, and then we'll continue with 2 more pieces, the continuous distributions and a little bit of hypothesis testing. So I'll leave the screen up. If you have any questions at this point, feel free to post them in the chat box, and we'll start the class at 11:30, having a look at the questions. So see you at 11:30. Back. While I wait for people to come back online and switch on the video camera, there was one question that arose during the break that I will quickly go back to. So the question was about the lymphocytes example for the binomial distribution. The part of the question that had to do with at least 2 lymphocytes. So this is also worked out in the version of the slides that are already posted online. But we can summarize that real quick by saying, well, if we want to have at least 2 lymphocytes, then that's the same as saying, well, 1 minus the probability of having at most 1 lymphocyte. So let me write it a bit differently. Lymphocyte number being less than 2. And if you write it like that, now you're in luck because you can calculate it by hand or with R. So you get that this is, and let me write it also as the probability, 1 minus the probability that there's no lymphocytes minus the probability that there's exactly 1 lymphocyte. And then if we do this by hand, then given that we're working with the binomial distribution, we have 10 choose 0. No lymphocytes means 0.20 to the power 0. And then the complement, which is 0.80 to the power 10. And then the probability of 1 lymphocyte, that's 10 choose 1. And then we have 1 lymphocyte, so 0.20 to the power 1. And 9 cells that are not lymphocytes, so 0.80 to the power 9. And just to simplify this a bit further, 10 choose 0, that's 1. 10 choose 1, that's 10. And so with this, you can calculate everything. Or you can be lazy and just use R for this. Of course, for this example, that's not necessary, but you could if you wanted to. And in either case, what you should get is, okay, I don't have the number, so I will type it in real quick. So either way, you should get 0.6242, 624, and so 62.4%. And the command here that I gave in R is 1 minus P binomial 1 out of 10 with a probability of 0.20. Yeah. So yeah, with R, the commands, they're always the same. P for the cumulative density, D for the actual density, and so on. We already saw P Poisson for Poisson. Here we also have P binom for binomial distribution. So with that, we can get started with our continuous probability distributions. This is also going to be more or less of a recap of things that I think you already know, either instinctively by thinking about it or by virtue of what we've seen in the section about hypothesis testing and before. So to set the stage, we'll say that a random variable is continuous if it can take on all possible values in an interval. So for instance, x being the height of a random person is a continuous random variable because height is continuous between 0 centimeters, let's say, and 2 meters and 20 centimeters. All possible values in between that are admissible. And now you might say, well, hey, but we never measure a height like 16 digits after the comma. We always measure it to the nearest centimeter, let's say, but that is immaterial for the definition. That's just a limitation of our measuring process. What matters is that that thing that we measure, the height, there's no reason why it should be quantized. It's a continuously varying variable. And what does that mean for the probability distribution? Well, for a discrete variable, we had that the probability was concentrated on a number of values. So, for instance, if we have a Poisson variable, then we said, well, the probability of having 1 count, 2 counts, 3 counts, 4 counts, and so on is some value, say, like this, and then so on. For a continuous variable, now we still have that the outcomes are on the x-axis. So, for example, height is, again, a good example to keep in mind. But now we can't assign probability to a fixed value. We can't ask, what is the probability of being 1 meter, 75 centimeter, 0.1234, whatever. It doesn't make sense to ask for a probability of one particular value. What we have to ask for instead is, what is the probability of having height in a certain interval? So, for instance, what is the probability of being between 1 meter 50 and 1 meter 75? And what that means is that probabilities in this case are described by a density curve, which is usually, but not always, a continuous curve. So here we have a density. And then rather than asking for the probability of a given event, or the probability of a given value, let me put it like that, we're going to ask, well, what is the probability of having an outcome between value A and value B? So we typically ask for what is the probability that P, or random variable, is between A and B. And the density curve allows us to answer that question because it's set up in such a way that that probability is precisely the area under the curve. And if you say area under curve, that sounds like integrals, then I have good news for you. It's exactly going to be calculating integrals. So a couple of density functions. So first off is the uniform density. So the uniform density is described by the density curve that you see on the figure. And this is typically some kind of, I have to be careful not to use too much terminology, but something that looks a bit like a function with steps in it. So I'll call it a step-like function. So it's something of the form, this is my axis, something that's 0 everywhere, and then jumps to a fixed value and stays flat, and then goes back to 0. So that's typically what a uniform density looks like. If we look at the example on the graph here, we see exactly that, the sort of the top hat. It's 0 until you hit -5, and then it becomes 0.10, and it drops back to 0 at x is equal to 5. So we can describe this function, this density function, by saying fx is 1/10 for, actually, let me, not going to have enough space there, so let me put it over here. So this density is described by f of x, which is 1/10 for x between 5 and -5, and 0 otherwise. So piecewise function prescription. And where do you use a uniform density? Is basically when you have a continuous variable where all the outcomes are equally likely in an interval. So let's say you're looking at a pond. And you're looking at a pond and it starts to rain. And your pond is nicely irregular, it's nicely rectangular. And so you have an X direction and a Y direction in your pond. And you look at the X or the Y coordinates of the raindrops in the pond. Then what you'll see is that there's no preference. The raindrops just drop at random, and they're not going to accumulate in a particular area. They're just going to be uniformly spread out over the pond. So in that case, if you wanted to model that, you would use a uniform random variable or a uniform distribution. So I'll write that down as raindrops in a pond, or raindrops on a tile in the pavement, where you have a nice rectangular area, and then the raindrops fall at random all over the pond. And if you look at the X coordinate, you'll get basically that the X coordinates are also random. There's no pattern in them. There's no accumulation anywhere. So this will be described by a uniform distribution. Let's maybe skip ahead just one slide. And while we're looking at this, let's do a calculation with this distribution. So we have the red shaded area between -3 and 1. And let's compute the probability of having something in between those values. So the probability that x is between -3 and 1. So I already mentioned on the previous slide, that is the shaded area, that shaded rectangle that you can see. You can calculate what that is, but let's just use the definition. By definition, that's going to be the integral from -3 to +1 of the density function. So 1/10 dx. Now, if we calculate that, that's 1/10 times 1 minus -3. So that is 4/10 or 2/5. So 40%. Very straightforward calculation, but I just want to show how these areas come in. What does that 40% mean? If you throw a dart at the x-axis and you close your eyes so that it's more or less uniformly distributed, then with 40% chance, you'll end up in this interval compared to the whole extent of the range from -5 to +5. Another distribution that we've already seen quite a lot is the normal density. So here you have that typical bell shape that we know. And here too, we've seen this when we calculated in semester 1, p-values. P-values are probabilities of finding data that's at least extreme. And in order to do that, we had to look at areas underneath the curve. So we'll put this aside, but I just want to point out that the normal distribution also generalizes to or is related to the student t distribution. So the student t distribution is another example of a continuous random variable. And then now that we know more or less what continuous random variables are, how do we calculate with them? Well, our events in this case are going to be intervals, and we're always going to ask, what is the probability of our random variable taking values in a given interval? And think like we will never ask, what is the probability of the random variable being exactly equal to this value? Think a little bit about playing darts. If you play darts, you throw the dart at the screen. You don't care what the exact position is where the dart ends up. If someone said like, well, hitting the center of the bullseye is going to be very unlikely or not, you don't really care about that. What you have is that the dartboard is subdivided into areas. And typically what you care about is, well, what is the probability of ending up in the center, or what is the probability of ending up in this area, and so on. So that's a bit the analogy that you have to keep in mind. So it's always probability of having values in an interval. And as it says on the slide, well, what is that probability given by? Well, it's the integral of the density function. So the f of x here is the density function. And you integrate that over the interval that you care about. So in this case, we're always going to do one-dimensional things. So it's going to be a simple one-dimensional integral from a to b of f of x. So we've already done one of those with the uniform distribution, but you can also now plug in your Gaussian, your normal distribution, or your t, and try to calculate those integrals. And given that integrals of probability densities are very important, people have sort of abstracted that out into a function with a special name called the cumulative distribution function. And let's focus first on the definition. So the cumulative distribution function, capital F of x, what is it? Well, it is the integral of the density function starting at minus infinity and going all the way to a fixed value x. So the x here that you see here, that's the argument of the density function. So graphically, what do we do for the density function, for the cumulative distribution function, is we take our density, let's say, looks a bit like this, looks a bit normal. And let's say we want to compute the value of the cumulative distribution in this point here. Let's call this x. Then what do we do in order to find that value is we calculate the area under the curve to the left of x. So this entire area, this is going to give me f, capital F of x. And now if you let x vary, if you change x, then of course that area is going to change, but that's what defines the cumulative distribution function. And now what does that mean for probability theory? We already said that areas under the curve are probabilities, And so what the distribution function encodes is, what is the probability of having a value between minus infinity and our little x? So in other words, what is the probability that our random variable takes on values less than or equal to little x? And then one last twist here, or one useful calculation property is, we know how to calculate probabilities that our random variable takes values in an interval. We said, well, hey, that's the integral from a to b of f of x dx. And now we can write that integral as two integrals from minus infinity. We can say, well, it's the integral from minus infinity to b of f of x dx minus the integral from minus infinity to a of f of x dx. And if you write this probability, which is this probability right here, if you write it like this, then you see the cumulative distribution function appearing 2 times. So this is f of b, and this is f of a. So we see that the probability of having values in an interval is the density, the distribution function of the upper bound b minus the distribution of evaluate on the lower bound a. And now you say, well, great, that means I only have to know the distribution function to calculate probabilities. That is true. Sadly, computing this distribution function is sometimes not explicitly possible. Sometimes you have to leave it as an integral and you have to use R to calculate it, or you have to use the table at the back of the course notes. So with that, we can now look at the summary statistics of random variables, just like we did for discrete variables. And we can talk about the mean. So for discrete random variables, this was a sum. We said the mean is equal to the sum over all probabilities times the outcomes. Let's say there are n of those. Now that we're in a continuous land, sums are going to become integrals because we don't have finite number of values anymore. We have continuously infinite range. So our sum becomes an integral, as you see here. And then what we put in between as the integrand, you see an x, just the variable x, times the density. So that's what plays the role of the probability here. That becomes the density here. And we integrate from minus infinity to plus infinity with the convention that if the variable doesn't make sense for a certain range of variables, then f of x will be 0 there. And the interpretation is exactly the same as for discrete random variables. So this is a measure for the center in a way of the distribution. And in other words, and I'm pulling hairs a little bit here, the typical value. But you have to be careful with that because you know already if you have a skewed distribution with a lot of skew, then the center might not be close to where the mean is. So the example again being the the distribution of wealth in a country. If we ignore that wealth, or well, we don't have to ignore it. If we take wealth to be a continuously distributed random variable, then typically income levels are like this. You have a peak of moderately well-off people and then a very long tail of very rich people. And that tail is gonna skew the distribution, and maybe the mean will be somewhat here, whereas the typical value or the center of the distribution will be here. Let's say this could be the median in our the x-axis, we have the income. So we saw that earlier, but just to focus on it again. Same story for the population variance. So for discrete random variables, there we had that the variance was equal to the sum over all possible outcomes of probability of the given outcome times the outcome itself, xk, minus the mean squared. And here we see the same pattern. So integrals, sums turn into integrals. We have x minus mu squared. That's the same term or a similar term as what we had in the discrete. And then we also multiply by the density. That's the analog of multiplying by the probabilities. And the standard deviation of that is the square root of the variance. And what is the interpretation? So this is a measure for the variability of the distribution. So for instance, if we look at normal random variables, then if we compare two, this is a sketch. If I give you two distributions, one that's relatively peaked, and then another one that's broad and shallow, then typically here we would have that, let me use colors here, sigma squared, relatively speaking, small. And for this one, sigma squared, large, again, or larger, let me say. And just for the people that really like their mathematics, you can let, in the normal distribution, you can let sigma squared, it's a parameter, you can let that go to 0. And you can sort of think, oh, what is a distribution that's infinitely, like that has no variability, zero variability? Then what you'll end up with is something of the following form. That's infinitely narrow, so that has width 0, but that is infinitely high. And so what you'll end up with, so here we have, this is just a mathematical curiosity, sigma squared being equal to 0. So we have infinitely narrow and infinitely high. And if you've ever encountered the Dirac delta function in control theory or in a similar course, you'll get precisely one of those. But that's just by the by, that's just an aside. A couple of properties that I want to remind you of, which are useful, and we talked about these properties way back in the beginning before we even did hypothesis testing. But if you have random variables, you can combine them into new random variables. And in particular, what you can do is you can scale random variables. So if you have A and you replace it by A times X, that is a scaling. And what it ends up doing is that will not change the mean of, or the mean of the random variable. So if my density function looks like this, then what A is going to do is, or what scaling is going to do. Let me sketch something that's a bit more symmetric, like this. So this is the distribution of X. Then the scaling is going to leave the mean where it is. Let's say it's at the peak here, but it's going to make the distribution narrower if A is less than 1 and wider if A is bigger than 1. And likewise, what you can do is you can take a random variable and you can add a constant to it, and that is tantamount to translating or shifting the distribution. And what it ends up doing is, if you have a random variable with mean, let's say here, then the translated version is going to have the same shape, but just moved by a certain amount. So moved by B. And these two rules are summarized mathematically in this first rule here. So if you if you scale the random variable, and yeah, I have to be a bit careful here. So yeah, I may have to take another look at my intuitive explanation here, but let's focus on the rule for just a second. So yeah, if you scale, you end up scaling. Yeah. So actually, let me be a bit bold here and erase this. So I will draw a different picture here. I was trying to be intuitive, but I will replace this by another picture. Because yeah, what I drew is not correct. If you scale, you do change the mean, so that scaling factor just comes out front. So there is a picture that I can draw, but it is a bit more, it's a bit less intuitive. So, okay, just to try and draw something, let me draw it like this. So let's start from a distribution, and then let's do the scaling by A. And what you end up doing is, when you scale by A, you sort of draw everything closer to the origin, or you push it away from the origin. So you end up, if A is less than 1, you end up with something where our entire distribution sort of becomes, gets to be closer to the x-axis, and then like this. So for A less than 1. And for A bigger than 1, what you do is you sort of end up pushing away things from the y-axis, from the origin, by an amount that's proportional to how far away you are from the origin. So you end up with something like this. And here I also have to be a bit careful, like so. A bigger, and then the calculation works out. For the other three, I don't have a good picture, So if you add two random variables together and you compute the mean, you'll see that you get the mean, the sum of the means. And for the variance, we have a similar thing. So here, okay, our intuition does work out. For the variance in rule number 3, if we shift the random variable by a given amount, that doesn't change the spread. Like all we do is we shift things around. We don't change the appearance of the distribution. And if we multiply a random variable by a constant, then what ends up happening is that the variance is multiplied by the square of that constant. And that you can also sort of imagine from the figure. So if we push everything away from the origin, we make the distribution wider. And that's why there is a constant there in front of the sigma squared. And then the last rule says, if we add two random variables together and we compute the variance, then if the two variables are independent, if they're not related, if knowing one doesn't tell you anything about the other, then the variance of the sum is the sum of the variances. Then you can just add the two individual variances together. So we also know if x and y are dependent, so not independent, then we will see the correlation between the two playing a role. So then it'll depend on how the two variables are correlated to say something about the variance of the sum. And before we go to the next slide, just want to point out that all of these rules you can derive from the integral expression, the definition. Let's maybe do one. So, excuse me. If I look at the mean of ax plus b, then, and here I also have to be a bit careful. So let's simplify things a little bit. Let's do a calculation that's maybe a bit easier. So let's just shift x by a given constant b, and let's compute the mean. So what does the definition tell us? Well, it's the integral from -infinity to +infinity. And we have to take the x value and then multiply by the distribution of fx plus b dx. And so now what does that mean? Well, now we have to know what the distribution of f of x of b is. And this distribution is given by the distribution of x evaluated at the point x minus b. So in other words, if I just write this out and then we talk about it, I get fx x minus b dx. Why is this thing that I squeeze in, why is that true? Well, look back at the figure. If I add a given constant b to my random variable, what I end up doing is I shift my distribution function by a given amount b. So the shape of the function stays the same. It's just all shifted by b. So if this function right here, the black one, is fx of x, then the blue one, fx plus b of x, is fx, the original distribution function, shifted over b units. Okay, so now with that we can conclude we can finish off our computation. So we'll do a small substitution in the integral. We'll call this u. And then what we get is the integral of from minus infinity to plus infinity u plus b f of u du. And okay, now I'm running a bit out of space. So I will try to finish it in one go. Don't want to skip any steps, so I will write this out as integral of u f u du plus integral b times integral f u du, and that gives us almost what we need. The first part here, integral of u f u du, that is the mean of x, and then plus the other integral. So here we have integral of f u du, that is equal to 1, because the total area under the curve has to be equal to 1. So we get plus b here. It's a little bit messy because I had to squeeze it into the slide. If you want to see the calculation being done again with a bit more attention for detail, I will refer you to the course notes, but this is sort of the, and it's in chapter 4, so quite a ways back. But these are the main steps. So now I want to, for the last part here, return to the normal distribution. And this is just going to be focusing on some terminology again, so we're not going to do any calculations. So we have this, the density here of the standard normal distribution, so the bell curve that I already mentioned. And it is 1 over square root of 2 pi times e to the minus x squared divided by 2. And the defining characteristic of the normal curve, the thing that's worth keeping in mind is that if you look at the area under the curve, there's the 68, 95, 99.7% of the rule. So 68% of the distribution is 1 unit away from the mean. 95% is 2 units away from the mean, and 99.7% of the distribution is 3 units away. So again, that's why sometimes in popular parlance you hear people talk about a 3 sigma event is somewhat unlikely but still possible, but a 5 sigma event, a 6 sigma event is way out here or here, and very unlikely. We can calculate the population parameters of the normal distribution. I will not do that just for lack of time, but you can do that as an exercise. It's basically just an integral. So for mu, you have that this is the integral minus infinity to plus infinity x times 1 over square root 2 pi e to the minus x squared divided by 2 dx. And of course, the 1 over 2 pi can be taken outside. And so now you can solve this integral exactly. And does anybody want to give me maybe you can drop it in the chat or speak out. How would you solve this integral? Any takers, any suggestions? Is there anything that you sort of would do right away when you're confronted with an integral of this form? Yeah, so I get suggestion from Jaemin Lee to substitute, and that's exactly what you should do here. So you have x squared over 2. If you call that u, you get x squared over 2 is u, du is x dx, and then you see an x and a dx here, so that combines nicely. And in this way, you can solve the integral. You just have to be a bit careful because the boundaries here are minus infinity and plus infinity. But if you do all of that, just a simple integral, then you will find the result of the course that it is 0. And likewise for the variance, same integral more or less, but just a bit more work. You'll find that the variance is 1. And then the cumulative distribution function, so the integral from minus infinity to a fixed value z, is given here as an integral because this is one of those functions where we can't compute the integral. So if you want to know what the cumulative distribution function is, you'll have to ask R or the table at the back of the book. And then just to wrap this up, the general normal distribution is basically what you get if you take a standard normal distribution and so standard normal distribution with mean 0 and standard deviation 1, and you first translate by mu, and then secondly scale by sigma. And if you do that mathematically, then you get something like this for the density function, where now we have x minus mu squared instead of x squared, and we divide by 2 sigma squared instead of just 2. And this, if you do the same calculation as we had before, or if you think about a bit what translation and scaling means, then you'll find that, yeah, mu, this parameter here, is the population mean, and sigma squared is the variance. And last, we can also go back. If we have a general normally distributed random variable x, then we can turn it into a standard normally distributed variable by, the recipe that you've seen before. You subtract the mean, mu, you divide by the standard deviation, and you end up with something that has mean 0 and standard deviation 1. And here, yeah, you see various random or various normal density curves. The ones that are broad and shallow have high standard deviation or high variance. The ones that are peaked and narrow have low standard deviation, relatively speaking, of course. The same property, the 68, 95, 99% rule, holds for general normal distribution, except now instead of saying 1 unit from 0, it's 1 standard deviation from the mean, 2 standard deviations from the mean, 3 standard deviations from the mean. So I will skip over this. And then to finish off, just a philosophical note about the normal distribution. So why do we care so much about the normal distribution? That is maybe a question that you ask. And that is a very good question. And the answer lies in something that we've seen before, namely the central limit theorem. So if you add a lot of random things together, then basically what happens is that they will sort of more or less cancel out, and it'll give you something that's nicely normally distributed. And that's why we care so much about the normal distribution, because in nature, in biology, in production processes, you typically have a bunch of little things that add up together and form a normal distribution. So you see the normal distribution occurring over and over again. But it's very important to know that not everything is normally distributed. And here what I've drawn is a normal distribution in black, and then a normal distribution in the dashed line, and then a Cauchy distribution in black. So this is the so-called Cauchy distribution. And we haven't seen its density, but the density is basically 1 over pi, 1 over 1 plus x squared. So very, very simple distribution. But this is a very pathological distribution. And why is that? Well, you see, for instance, if you look here at the tails of the distribution, that the normal distribution goes to 0 very quickly, and the Cauchy distribution goes to 0 relatively slowly. So this is a phenomenon known as fat tails. And here too. And what does it mean for a distribution to have fat tails? Well, it means that extreme observations are relatively likely compared to the normal density. So remember, with the normal density, we expect 99.7% of the density to be between 3 standard deviations of the mean. So 99.7% of the data is in a very narrow range. And with the Cauchy distribution, that is not the case. The range of possible events, the range of likely events is much larger, and in fact turns out to be infinite. And this occurs sometimes in mathematical modeling of natural phenomena. Maybe you have read this book that was very popular maybe 10, 15 years ago called The Black Swan, where the author was making a case for, hey, we had this gigantic financial crash, and it arose basically because people thought, oh, financial phenomena are normally distributed, and I understand the normal distribution. But he was arguing like, hey, there are a lot of things in nature that are not normally distributed, where you have a very likely chance of extreme events happening. And so the Cauchy distribution is sort of the poster child of that, where you can have large events taking place with high probability. And I have a mathematical challenge for you, which you can do or not do if you choose in your spare time. But I want you to calculate the mean of this distribution. And what you'll find is, if you solve this integral carefully, you'll find that the mean of this distribution does not exist. And if you're extra brave, you can also calculate the variance, and you'll find that the variance also does not exist. So this tells you that this is a distribution to be careful about, because you say, what do you mean the mean doesn't exist? It's a nice symmetric distribution, and the mean is going to be the center here, so the mean must be 0, right? No, that is false. That is not true. The typical value of this distribution is not 0. The typical value of this distribution does not exist. And maybe just one last thing to drive home the point. You can say, well, what if I compute the mean by just taking samples from the distribution? Like, I'm not going to try to calculate this integral. Like, I know it doesn't exist, but I'm going to put on my data scientist hat, and I'm going to take observations from this distribution, and I'm going to add them all together and divide by the number. So in other words, I'm going to calculate an empirical mean. Then I'm going to get a number out, right? So won't that number be some kind of approximation of my mean? If you do that for the normal distribution, then I will agree with you. What will happen is, if you sample from the normal distribution and you average out, you'll get something that's very close to the mean. So no problem there. If you do this with the Cauchy distribution, you take sample after sample and you average them out, then what you will see is that your average will converge to a number, but occasionally there will be a big new observation, an extreme observation, which will completely destroy your average. And over the long run, you'll never settle on anything. You'll think that you have some kind of pattern in the data, and then there will be a sort of a push away from that data. And I'll leave you to sort of think a bit about societal implications. If you're, for instance, investing in your portfolio, you probably want to have some kind of prediction of your rate of return. You want to know, like, okay, my portfolio is going to increase over 3% over the course of X years. You don't want a portfolio that is determined by the Cauchy distribution, where you say, oh, it looks like it's going to average 3%, and then there's a war in Ukraine, and all of a sudden it's minus 20%. Or there's something really good and it's plus 50%. You want nice, steady, predictable results, not something that can change with arbitrary magnitude. That's why I bring up the Cauchy distribution, just as an example of a natural phenomenon or something, a class of phenomena that is not entirely captured by the normal distribution. That's a complete aside. We will not do anything with the Cauchy distribution from this point, but just be warned and be forearmed, for example. Okay, so with that, we are done with the normal distribution, and there's just a little bit of material left about hypothesis testing for proportions. Before we dive in here, any last questions about what we've covered so far? Dump them in the chat or raise your hand if you have any. If not, we will wrap up this entire chapter on probability by talking about hypothesis testing for proportions. Okay, so why hypothesis testing? Well, we want to go back to our random variables, and now we want to do something useful with them. Remember, when we do statistical inference, what we want to do is we want to draw conclusions from random data. We don't just want to describe the data and say, oh, it follows this distribution or that distribution. We want to say, I know what this parameter is, and I am 95% confident about it. Or we want to be able to say, this population and that population are different at the 5% significance level. So in other words, we want to draw conclusions from our data. And we have a bit more machinery in our toolbox now to extend the range of tests that we can do. And I have to say at this point, what I'm going to talk about is also a recap of something that we saw at the end of chapter 5. So if you studied hard over the Christmas break and you looked at chapter 5, none of this will be new. It's maybe just reinterpreting it, knowing what we know about random variables. So what I'm going to do is I'm going to use an example here to set the stage and to introduce the general theory. So we'll put on our hats of quality control inspectors in a food factory. And we're visiting today a factory that makes mandu. And we know that the production process is so that on average, 10% of the mandu that the factory produces have some kind of imperfection, which makes them impossible to sell. So we have to be discarded. So 10% defect rate, 10% wastage. And we're inspecting our factory, and we take a random sample of 500 mandu, and we find that 64 out of the 500 have imperfections. And now we wonder, well, okay, 64 out of 500, what proportion is that? How confident are we about that proportion? Can we give a confidence interval? And is that percentage that we observe, is that significantly different from the target rate of 10%? Should we be telling our boss, hey, actually, there's something going on. It's not 10% anymore. It's significantly different, and we need to either fix the machine or take into account that, yeah, now it's 12% or something. So let's try to answer those questions within the framework of hypothesis testing. So we'll make a couple of assumptions. First of all, this is a simplification. We'll assume that each Mandu has a fixed probability of being bad, of having some kind of imperfection. And we'll call that probability P. And P, we don't know what that is. That is what we want to know. And then the other assumption that we'll make is that all Mandu that we produce are independent from one another. So if we have a failure for one Mandu, then that does not influence whether the next Mandu that comes out of the machine is going to be a failure or not. So they are completely independent of one another. You can quibble with this assumption. This is probably not true in real life. If there's some defect in the machine, maybe they're all related, they're all defective, all the Mandu have blemishes on them, but we'll make this assumption just for the sake of it. So for our first question, we're interested in the proportion of rejected Mandu. And how can we compute that? Well, we can count basically the number that were rejected and divide by the total number that we observed. That's what you have at the bottom of the slide. We had 64 rejects, 500 in total. That's about 12.8%. Before we get to that number, or to unpack that a little bit more, what can we say about the proportion of rejected Mandu in general? Well, we can write that according to the expression that I have here, where the proportion that we're after, pi, is given by this sum in the denominator, where we have n random variables, one for each Mandu, so 500 if we take a sample of 500, and x is 1 if the Mandu is a reject, and 0 if it's not a reject. So here, keep in mind that n is equal to 500, so that sum on the top is x1 plus x2 plus ... plus x500. And for instance, x2 is 1 if we reject Mandu number 2, and it is 0 if we do not reject. And same for x1 up to x500. And why do we write it like that? So if we write this summation here, so this summation is going to have terms that are 1 for the reject, 0 for the not reject. So the sum, the total sum that you have in the numerator here, that is the count of rejected Mandu. And that should ring a bell, because count of rejects, where we have a probability P of having a single reject, so that is a binomial variable. So what that means is that the sum of all of these things, xi, is binomially distributed over n trials with probability P of success. And here, once again, n is 500 and P is unknown. And so just to wrap up the pi, so if we know the count, that sum, then we divide by n to turn that count into an average. And in this way, to wrap up a long story, that pi thing that we have is a random variable in itself. And what does that mean, that it's a random variable? It basically means it is a function of the sample that we take. If we take another sample of 500 Mandu, we're probably going to see a different rejection rate or a different percentage that was rejected. So the pi that we've defined in the middle of the slide takes into account the sample and then gives us a number for that sample. So on the one sample that we have data about, the one where 64 out of 500 were rejects, the value is 12.8%. So that satisfies our first question, but it's not enough. Our boss might say, well, yeah, you got 12.8%, but that doesn't mean that the machine is broken. It just means that, yeah, we were unlucky. You need to convince me that that is really a representative value. So that takes us to the second part of our question, where now we want to build a confidence interval for that proportion. And for that confidence interval, we're going to exploit an observation. We're going to come back to this expression, and we're going to observe that this expression, so the right-hand side here, looks like a mean. And why does it look like a mean? Well, we're summing a bunch of things together and we're dividing by the count. That's a mean in my book. And how does that help us with a confidence interval? Well, we know that from the central limit theorem, if we have a mean over a lot of things, that mean is going to have its own distribution, and that distribution is going to be a normal distribution. So here we are invoking the central limit theorem to say, well, the sampling distribution of the mean is a normal distribution. And now normal distribution by itself has two parameters. It has itself a mean and a variance that we call the standard error of the mean. And we can actually write down what those are. So we know that on average, the random variable pi, its mean is going to be the proportion that we're interested in. And why is that? Well, in order to figure that out, we have to go back all the way to the beginning of hypothesis testing. If we ask for the expected value of pi, then that is the expected value of the sum of all of those x's divided by n. I can take out the 1 over n. I can also take the sum out of the expectation value. And now I know that each of these xi's, which told me that is Mandu I defective or not, that happens with Mandu I being defective or not happens with probability p. So the expectation of each individual Mandu being defective is p. And now I don't just have one Mandu, I have n Mandu, I have that summation. So I get n times p divided by n, which gives me p. So that's why I end up with mu being equal to p. And then for the variance, it's the same thing. So what is the variance of pi? So now that is the variance of the summation divided by n. And now I have to be a bit careful. If I take out a 1 over n, that becomes a 1 over n squared, because multiplying a random variable by a constant, you can take that constant out, but it becomes squared. And now I have variance of sigma xi. I've assumed that the Mandu are independent. That was my assumption. So I can take the summation out of the variance. And let me maybe continue over here. I get that this is 1 over n squared summation variance of xi. Xi, again, is a binomial variable. So I know what that is. This here is equal to P1 minus P, because it's a binomial random variable with n equal to 1. And now I still have the sum, so I get n times Pn minus P, which is P1 minus P divided by n. And if I take the square root of that, I get precisely this expression right here. So this, the sigma here, is a measure for how accurate my estimate of the proportion is. And now I can combine these two. I can say, well, I can build up a confidence interval for the proportion by saying, well, what is the confidence interval? Well, it is my estimate then times a quantile of the normal distribution, and then times the standard deviation where I substituted P is pi. So what I'm basically doing is I'm looking at the distribution of pi, that is a normal distribution. The mean is P. The standard deviation is given by the expression that I have here. And then I define my confidence interval as everything around the mean 1, 2, 3 standard deviations away. Okay, so let's plug in some numbers and let's see what that tells us about our Mandu. So in our example, we want to have a 95% confidence interval. So the quantile that we have to look at for the normal distribution is Z 0.975, which if you plug it into R or if you look into your table is 1.96. So that, remember, that is a very important variable or a very important number. This basically means that in your normal distribution, if we ask for 95% of the data, like so, then we have to go to plus 1.96 and minus 1.96, like so. We can also compute the, and let me call this sigma here to have the same notation as on the previous slide. We can compute the standard error of the mean or the proportion with the formula from the last slide, and that'll give us 0.0149. And then if we multiply everything together for the confidence interval, we get this expression, which works out to about 9.9% up to 15.7%. That's our 95% confidence interval. So if we go back to our boss, we can say, well, it looks like we are 95% certain that it is between those two values. So in particular, you see it is higher than 10%. And then if you just give me 2 minutes to wrap up, I mentioned that this definition or this approach is valid if n is large enough. So then we get our normal approximation and then we're in business. Now the question is, how large does n have to be? There are many different conditions in different books, but we will use the following condition. So the probability that you look at times the sample size times 1 minus the probability has to be larger or equal to 5. If that's the case, then you can use the normal approximation without any trouble. I've also shown here the difference between the normal approximation and the exact approximation. So the red is the normal approximation and the blue is what you would get if you calculate it without the normal approximation, so exactly. And you see some differences here and here, but on the whole, it's a good fit. The normal approximation here works. And then the last thing that I want to point out, and this is going to be useful for the exercises on Thursday, is we can also turn this insight into a hypothesis test. So here for the hypothesis test, we have to formulate a null hypothesis where we say the population proportion is equal to a fixed value. For instance, the proportion of rejected Mandu is 10%. That's our null hypothesis, the status quo. The alternative hypothesis, if we do a two-sided test, could be it's not equal to some fixed value, it's different. It's not 10%. And what we can do to test that hypothesis is build the following test statistic. So we take the value that we obtain. So this is our point estimate. In this case, pi was 12.8%. This is the value from our null hypothesis. And this right here is our sigma. And if we combine these variables, we get a z value that is normally distributed, mean 0, and standard deviation 1. And once you have this test statistic, then you're in hypothesis testing land, because now you can compute p-values and you can actually draw your conclusions. So to wrap this up, and this is the last thing that I'm going to talk about, let's draw the conclusion. So the conditions that we need for a hypothesis test is the observations need to be independent, yes, by assumption. Our normal approximation needs to hold. So we have to have that this combination is bigger than 5. It's 45. So yes, that holds. If we compute our test statistic, then we get 2.087. And that corresponds to a p-value of 0.037, so 3.7%. So remember, the p-value is what you get if you take your normal distribution, you grab your test statistic t here, and then you ask for what is the probability of having even larger values than t. So what is the area under the curve here and also here at minus t for a two-sided test. So in this case, we would go back to our boss and say, we observed a 12.8 deficiency rate or defect rate, and we do have statistical reason to believe that that is significantly different from the 10% defect rate that we started from. I will skip this. What if the normal approximation doesn't hold? Well, if the normal approximation doesn't hold, then you can go back all the way to the beginning. You can think about the fact that the count of Mandu that are rejected is a binomially distributed random variable. And then you can use that and the fact that you can calculate now with binomially distributed random variables to compute the p-value exactly. And if you do that, then you will get a p-value of 0.025, so a bit lower, which means that you can be a bit more confident in your statistical conclusion that it is that our defect rate is significantly different from 10%. We will not do this exact hypothesis testing. It is sufficient if you can use the normal approximation. So with that, I will stop here because I've gone overboard for 5 minutes already, and it is high past lunchtime. I will stay on for a couple of minutes to convert the recording and post that online. But if you have any questions, do feel free to either post them now or if not, then via email, and I'll get to them next time. So thank you very much for your, oh, I see one question. The feedback for project 1 will be released this week. And I will provide either in writing or during the course also some general guidelines for project 2, how to approach that. So stay tuned. Probably before the end of the week, you will have some feedback. So thank you, everybody, for your time, and I hope to see you next week as well. Bye, everybody.